In today's episode, we will design a circuit that compares two voltages and decides which one is bigger. Hi, I'm Art Edang and welcome to this video of Tinker Tinker, where we examine circuits, play with their equations, and make our designs work. There are many situations where we need to automatically turn on or off a device when something happens. For example, we may want a street lamp to turn on when the sky gets dark. In this case, what we need is a comparator circuit, and we can readily make one by using an op-amp. An op-amp is an integrated circuit which takes in two input voltages at its inverting and non-inverting terminals and gets the difference between them. Then it amplifies the difference by a very large number and produces an output accordingly. In terms of an equation, we can express this behavior as Vout equals A times V positive minus V negative. For example, let us say that we have the following values. Using the formula, this gives us Vout equals 150 volts. Now that is a very large voltage and should make you wonder if it is at all possible. To answer that, let me say that the op-amp is usually powered by two voltage sources, positive VCC and negative VEE, which limit the output of the device. For instance, if our VCC equals 5 volts and VEE equals negative 5 volts, the output will be within that range so that instead of 150 volts, it will just be positive 4 volts. But more importantly, you will observe that Vo will always be the same value, let us call that as Vout high, whenever V positive is greater than V negative. And so we can generalize this behavior by this principle. Vout equals Vout high whenever V positive is greater than V negative. If this condition is not met, then we have the alternative behavior. Vout equals Vout low whenever V positive is less than V negative. And let us add that Vout high and Vout low depend on the values of positive VCC and negative VE, respectively. Okay, now let's see how the comparator will behave if we give it a varying input signal. For V positive, let's use a sine wave which swings from positive 3 volts to negative 3 volts. For the other input, let's set it at 1 volt and call it as the reference voltage Vref. According to its operating principle, the comparator's output will be Vout high whenever V positive is more than 1. At other times, Vout is equal to Vout low. Let's observe how our waveforms will look like. Channel 1, the orange line, shows the sine wave that is present at V positive. Channel 2, the blue line, shows the output of the comparator. Notice that whenever the wave is more than 1 volt, that's our Vref, the output is positive, Vout high, that is close to 4 volts. At other times, when the wave is below 1 volt, the output is negative, close to negative 3 volts, which is our Vout low. Next, let's modify the circuit by making V negative equals Vref equals 2 volts. Okay, let me give you the chance to think about this. How will Vout be different from the previous circuit? You can pause the video before I give you the answer. So this is the output at Vref equals 1. And this is the output at Vref equals 2. Congratulations if you figured it out. You are or soon will become a good circuit designer. Notice here that Vo appears a bit thinner and is positive for a shorter time now. This means that the sine wave stays below 2 volts for a longer time. Now instead of waveforms, another way of representing the comparator is by showing its transfer curve. Here the vertical axis represents Vo, while the horizontal axis represents the input. In the left graph, we see that VO is VO low when VI is less than 1 volt, and it is VO high whenever VI is greater than 1 volt. In either case, 1 volt is the reference voltage that is connected at the inverting terminal. The graph on the right is similar, except that the transition happens at Vref equals 2 volts. For the same circuit we showed earlier, the transfer curve is now included for Vref equals 1 volt and for Vref equals 2 volts. Now that we've learned how a comparator works, let's try out another source of input. In real-life applications, we use sensors to measure different physical quantities as shown in the table. For today's episode, we'll use an LDR, a two-terminal device whose resistance value decreases as the intensity of light increases. For this episode, I used the smaller LDR with a diameter of 3 mm. I measured the resistance at two conditions, when it was bright and when it was dark. To keep the numbers simple, I will round them off to 2K ohms and 4K ohms. Then I connected the LDR to a fixed voltage source in series with a resistor. Take note that the circuit is a voltage divider, so that when it is dark, the input Vi is given by VID. Then when it's bright, the voltage becomes VIB. But the important thing here is to realize that Vi is inversely related to intensity of light. Okay, we now know about the comparator and also the LDR. It's time to play with what we just learned. So the challenge now is to design a comparator circuit so that an LED turns on when the LDR sees darkness. There are hundreds of op-amps available in the market, but for today, we will use the LF353 from Texas Instruments. This IC has two op-amps inside it, but we will use only one for now. Next, I will use the analog discovery module to power up the op-amp. This particular unit provides positive and negative 5 volts, aside from the built-in oscilloscopes and function generators. Then we return to the combination of R1 and the LDR. Actually, there are lots of values of R1 which we could use, but what we want is a large difference between VID and VIB, as the light changes from dark to bright, or vice versa. Now why is that? Let's consider two possible waveforms of Vi. The orange Vi line varies from 2.20 up to 2.60. With a green Vref of 2.40, there is a distance of only 0.20 volts from either the positive or negative peaks of Vi. Compare this to the blue Vi line, which shows a distance of 0.40 volts from Vref. Now, it becomes obvious that the blue line is less likely to be misinterpreted by the comparator whenever there is noise. And so now I will show you how to get the value of R1 from the difference of VID and VIB. Technique number 1. Use a spreadsheet calculator. Knowing the values of RD, we will first calculate VID. Then using RB, we will calculate VIB. Then, we get the difference between them. For R1, substitute the commercial values that are available. Then look at the trend of the difference and notice that the highest point occurs for two values of R1, 2.7K and 3K. Technique number 2. For those who have studied differential calculus, you will recall that the maximum value of a function is found by getting its derivative and equating the result to 0. So I get the difference between VID and VIB and simply call it diff. Then I get its derivative with respect to R1. Then equate it to 0. By a little bit of algebra, I get the equation for R1. Then I substitute the values for RD and RB, and I get R1 equals 2.83K. And the closest commercial value available is 2.7K. Notice how this result totally agrees with technique number 1. Now based on R1 equals 2.7K, we see here the numbers for VID and VIB. To get a value for Vref, just choose something that is halfway between them, close to 2.56 volts. So the question now is, what are the values of R2 and R3 that will give us something close to 2.56 volts? It's a voltage divider circuit, and I picked R2 equals 2K and R3 equals 2.2K. This gives us Vref equals 2.62 volts, which is, I repeat, close enough. We are now done with the input stage. Now consider the output. The LED turns on when it is dark, that is, when V positive is more than V negative, and V out equals 4 volts. When the environment is bright, VO is around negative 4 volts, which can destroy the LED that is in reverse bias. That's why we add a diode, a 1N4001, to protect the LED since it can handle as much as 50 volts. Let's compute. When VO high is 4 volts, that value will be split among 3 components. 2 volts for the red LED, zero point 0.7 volts for the diode, 1.3 volts across the resistor. Now how to get R4? The current through it should just be enough for the LED, that is around 20 milliamperes. Since VR4 equals 1.3, then R4 equals 1.3 volts divided by 20 milliamperes equals 65 ohms. The nearby commercial value is 68 ohms. The circuit is now complete and I have assembled it on my solderless breadboard. It's time to test it. Notice from the screenshot that Vi, the orange line, varies from around 2 volts to 3 volts. You will also see the change in the output. The blue line happens when Vi is around halfway between 2 volts and 3 volts. If we take a closer look, we will see that the maximum voltages of the LDR and the reference voltage have values that are close to what we have calculated in the previous slides. So there you have it, a good design of an op-amp comparator circuit. Thanks for watching. If you have questions or suggestions, do type in your comments below. And if you enjoyed this tutorial, don't forget to click the like and subscribe buttons. I hope to meet you in the next episode of Thinker, Tinker.